So welcome back. This is our lecture number 16, and now I'm going to talk about learning the Bayesian network from data using the maximum likelihood approach. So we have discussed a bit about how we could learn the structure of a Bayesian network from data. The first time that we mentioned this subject was when we were discussing classifiers based on the Bayesian network. And we saw the tree-augmented network that was a sort of a naive Bayes that we could learn the structure from data. So we know that the naive Bayes has a fixed structure, and it has also the strong assumption that every attribute is independent of the other attributes given the class. So the tree-augmented network is going to break these assumptions by allowing a more flexible structure and connecting attributes they have a high mutual information. So the approach was very simple. We computed the mutual information between pairs of attributes, and we used the maximum spanning tree to come out with a tree structure that connected all the variables in the network. And we're going to see in this lecture that this approach is one instantiation of a more general algorithm that we call the Chow-Liu algorithm. So the Chow-Liu algorithm will come out with some score that can measure the dependency between variables, and we're going to use the maximum spanning tree to induce a tree structure that's going to maximize this score. But of course, we don't want to be limited to learn tree structures, because we have Bayesian networks that are actually graphs. So in the second part of the lecture, we're going to study different approaches to induce graph structures. And it's going to be a little bit more complicated because when we are working with tree structures, all the tree structures, they have the same complexity. If we measure the complexity by the number of edges that we have in the graph, all the tree structures have the same number of edges. But when we work with graphs, we can start adding edges and making the model more complex. And we need to come out with a new score in which we're going to put together not just the maximum likelihood component, but also a complexity for the model. So let's get started, and we're going to start studying the three approaches. Okay, so far in this course, we have mostly assumed that the structure of the Bayesian network was given to us. And in the previous lecture, we had the task of giving this structure, we should learn the parameters for that structure. And we use the maximum likelihood principle. So we defined what is a likelihood function. That is basically the probability of each case given by the Bayesian network, by our current model. And we multiply those probabilities for each training example that we have in the training set. And we seek for the model that has the maximum likelihood. So we could interpret this as a search for the model that best explains the training set. And now we're going to assume that the network structure is unknown, but we're going to keep the same approach that we had before. So we're going to still look for the structures, the models that have the maximum likelihood. So we're going to see that the problem now of learning the structure will be connected to the problem of learning the parameters, because as we change the structures, we will also change the tables that we have to estimate from data, and we will need to estimate those conditional probabilities in order to compute the likelihood of the training set. So these two problems will be connected. We will search for the structure, and this will connect us to the maximum likelihood estimates for the parameters, and we're going to use these maximum likelihood estimates of the parameters to compute the likelihood of the training set, and use the likelihood of the training set to assess the quality of the current model. In this process, we're going to define a class of scoring functions, and we're going to show that by looking for structures that maximize those scores, we will be indirectly also find the structures that have the maximum likelihood. And during this lecture, we're going to assume that we have complete data. The problem of dealing with learning the structures with incomplete data is quite similar, but a lot more demanding in terms of computational resources. Okay, so let's start with one example. So we have this Bayesian network structure here, and I want to evaluate the quality of this Bayesian network according to a certain data set. So what do we do? So we have the data set here, and we have the structure there, and we need to compute the parameters. So the computing the parameters is going to be a sort of an intermediate step for the computations. So what we do, we're going to assume that we have complete data, so it's going to be easier. The only thing that we need to do is to compute the frequencies and fill in the frequencies in the tables. So for instance, just to take one simple example here, A. The variable A has the values true and false, and A equal true, you're going to be 4, 1, 2, 3, 4 in 5 cases, and not A going to be 1 in 5 cases. And we do this for the conditional probability tables. Once we have the parameters, we can compute the likelihood. So in this case here, I'm going to use the log likelihood that is more common. We know that the likelihood will involve a multiplication of the likelihoods for each example, and if you multiply those likelihoods for a large data set, we will come out with the problems with underflow. So the best approach here is to work with a log likelihood, and I'm going to do that. In order to compute the log likelihood, it's very simple. Just compute the likelihood and apply the log function. Here, I'm going to use the log in with a base 2 because you're going to connect this idea of a log likelihood with other measures that they have in information theory that are typically measuring bits. So they use the base 2 for the logarithms in these measures as well. So in order to connect them, we're going to use base 2 as well. But if you use a different base, the results are going to be the same. The numbers will be different, but the results are going to be similar. Okay, once we have the parameters, we can compute the log likelihood. That's going to be the log of the likelihood as we computed in the previous lecture. And we can transform this multiplication into a summation of the log probabilities, and that's going to be good because it's going to be easier to compute that. As we have complete cases, it's very simple to compute the likelihood of an example. So for instance, this guy here is our first instance that we have here. And we just need to go to the tables and pick up the correct values. So in this table here, I'm going to pick up this A true, B true. I'm going to be this 3 over 4. And for this table here, I'm going to take A true and C false. Then I'm going to be this 3 over 4. For this table, I'm going to pick up A true. There's going to be this 4 over 5. And for this table here, it's going to be 3, B true, and D true as well. Going to be 1 over 4. I multiply those numbers together. I have this number here. I compute the log of this probability. Is going to be this number here. As we are working with the likelihoods, these probabilities, we were interested in finding the maximum one. And for the log likelihood, we are also interested in maximizing the log likelihoods. So basically, the computation is going to be the same because the numbers that we're working here are numbers between 0 and 1s. The numbers that we are working here are going to be the numbers between minus infinity and 0. But in both cases, we want to maximize. So here we want to find a number that is the closest to 1 as possible. And here we are looking for numbers that are the closest to 0 as possible. So I'm going to do this for the first case, the second, the third, the fourth, and the fifth case. I'm going to have all the likelihoods. I computed the log likelihoods and I sum them together. So this number, minus 13.35, is going to be a sort of a score, right? So it's going to be a number that gives us the quality of this model, how well this model is explaining these 5 training sets. If we change the structure, you probably get a different score, a different log likelihood. So I'm going to show to you in the next slide. So just remember that we had here minus 13 and we have this structure here, but I'm going to change the structure. Okay, now we have a slightly different Bayesian network is still with the same 4 variables. And what do? We do the same thing. Once we have the structure, we need to compute those tables. As we assuming that we have complete data, those tables, the maximum likelihood estimate for those tables will be simply the frequencies that we compute from the table. Once we have computed all the CPTs, we can move on and compute the log likelihood. Again, it's going to be the same principle. The numbers will be different because the CPTs are slightly different as well, and we're going to come out with different likelihoods and the slightly different log likelihoods. At the end, we have this final score. Again, we use this final score as a single metric to compare these two structures. In the previous slide, we got -13, and now we have a -14. And the -13 is higher than -14, so we like more the previous structure than this structure. So the previous structure has a higher log likelihood, so we like that most. So if you were doing a search procedure and looking for which is the structure that we like most, we would prefer the previous graph. So this approach that we just described, it's quite demanding in terms of computational resources, because we needed to search for the structure, and when we have one candidate structure, we need to compute the parameters using maximum likelihood. And once we have the parameters, we need to take the dataset, measure the likelihood of each training case, and sum all the log likelihoods. So, and we change the structure again, we have to go through this process over and over again. So it would be much better if we have a sort of a score that we could measure between the variables, and using the training set in order to compute this score, and this score would give us an information of which variables should be together in the Bayesian network. So which variables we should connect in order to have a good Bayesian network structure. So I'm going to start with scoring measures that are applicable to 3 structures. And what I mean by a 3 structure is that each node will have at most one parent, right? So if we think about what we consider a tree, it's going to be something like this, right? So it's going to be a graph, and we can have nodes here and nodes there. We can have more nodes here, and so on. So when we think about each node here, we see that each node has just one parent they are connected to, and this guy here has again just one parent, and so on. So if we have this limitation of each node having at most one parent, we will have a Bayesian network that resembles a tree like this one here. And we're going to use a scoring function, the mutual information. And we haven't seen mutual information before a few times. It has this equation here, and we can understand as a measure of a dependency between 2 variables. So using the mutual information, it does make sense if you think about the Bayesian network as a graph that expresses the dependencies between the variables. So remember that when we have the variables connected, they are dependent. When we remove one edge, we are making an independence assumption about the distribution. So it makes sense to measure the mutual information between the variables and connect the variables that have high mutual information, because those variables, they have a high correlation, they have a high dependency. And we can leave the variables that have low mutual information disconnected in the tree structure. So if we use the mutual information as this score, we can change the way that we evaluate the structure. So before we have that idea of we have the structure, we look at what are the CPTs. For each CPT, we calculate the maximum likelihood estimates and use the maximum likelihood estimates to compute the log likelihood of the structure. But now what we can do is to use that score to measure the quality of the structure directly. In this case, what we're going to do is to sum over the families of the variables that we have. We compute the mutual information between the node and the parent. In this case, because we have this tree structure, each node has just one parent. So the quality of this structure G here, you're going to be given by this measure T score, you're going to be simply the sum over the family. So you're going to take this family here, and I'm going to compute the mutual information according to the empirical distribution, D, and I'm going to sum this value with the mutual information between these two attributes and the mutual information between these two attributes, and so on. So I'm decomposing the computation in several parts here, and this is going to be the quality of this tree. And finally, when we say that we are computing the mutual information in the empirical distribution, what we are saying is something that's very simple, is that when we compute this equation here, that we need to compute those probabilities here, 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 and here. We're going to compute those probabilities by using frequencies that we compute from the training set, and just that. And that is one very interesting result. So it's written here that we can show that trees having a maximal likelihood are those trees that maximize the T score. So basically what we are saying is that if we search for the T score and find a structure G that maximizes its T score, this structure is the same one that we would get if we maximize the likelihood. And that is a very interesting result, particularly because the T-score that we measure with the mutual information decomposes over the families of variables. So we're going to involve just the variable x and its parent u. And by selecting pairs of variables that have the maximum mutual information and putting those pairs of variables together in a tree structure, we are automatically also maximizing this T-score. So this is known as the Chow-Liu algorithm, and it is based on the maximum spanning tree. Right? So basically the maximum spanning tree is an algorithm that will return to us a tree structure that have a maximum sum of the T-scores by considering first the edges that connect the variables with high mutual information. So I'm going to discuss this algorithm shortly, but I'm going to first discuss what is the connection between the T-score based on the mutual information and the maximum likelihood estimates. Okay, let's just remind the definitions of entropy, conditional entropy, and mutual information. So I have here the equations for entropy, for conditional entropy, for mutual information. And we also discussed it in the previous lecture. Very briefly, we did not prove that, but there is a proof in the book that the log likelihood decomposes over the families of variables in this equation here. So what it's saying is that we can take the families of variables that are going to be the x and its parents u, and we can compute the conditional entropy. So the conditional entropy is this equation here, so we can compute for each family and multiply this by n, that is the number of samples that we have in the training set, and that is going to be our log likelihood. So we did not prove this, but it's also not a very surprising result, so it's not trivial as well, so it will require a proof, but it's not totally surprising, because we know that when we have a Bayesian network, the joint distribution will factorize over the families, right? So it's going to be a multiplication of the probabilities that are defined over the variables x and its parents u. And as the log likelihood is the multiplication of the probabilities of each instance, if we start with the log likelihood and we replace the probabilities of the instance by the chain rule of the Bayesian network, and we work a little bit with the equations, we're going to end with the conditional entropy. And also because we are working with the log likelihood that it has a log term, and the conditional entropy also have the log, so we see that there is a mathematical relationship between these two things at a high level. Of course, in order to show that is actually true, we need to go through a process of proving this relationship, but we're going to assume that as being true for now. And we can also take the multiple information and work a little bit with this equation here, and we can show, and this is a sort of a classical result, that the multiple information between, in our case, is going to be two variables only, because here, because we are working with three structures, the U here is not a set. Well, it can be understood as a set, but it's going to be a set of just one element, because we have just one parent for each variable. So the multiple information between these two variables, x and u, is going to be the difference between the entropy for x and the conditional entropy of x given u. And remind that we are using this d here because all those entropies, conditional entropies, and multiple informations that are being computed over the empirical distribution. Basically, it's a very simple idea. When we compute the probabilities, we compute them as ratios of the cases that we have in the training set. Okay, and now we can see that there is a connection between the log likelihood and the multiple information, because both are mentioning this same term here, that is the conditional entropy. So there is a connection between them, and I'm going to explore this connection in the next slide. Okay, let's put everything together in order to make a very short proof that connects the log likelihood and the t-score. So we know that the log likelihood, it decomposes over the families of the variables. So we're going to have this expression here. So I have minus n, reminded that n is the number of examples that we have in the training set, and it's going to be this sum over the families that we have in the Bayesian network, and we're going to compute the conditional entropy between the variable x and the variable u. And now that we have the log likelihood defined with the conditional entropies, we can use this property here, right? And then we have the conditional entropy here. So I'm going to basically isolate the conditional entropy on one side, and I'm going to replace this by this conditional entropy here. And now we're going to transform this equation into this one, where we have these two components here. We have the entropy for the variables x and the multiple information for the variables x and u. We can take this term here that is minus n and this sum and put that inside here, right? So we're going to have two sums. So the first term going to be this one, going to be a sum for the entropies of the variable x, and now we're going to have a second term that will be the sum over the families for the multiple information of x and u. If we analyze this expression, so now and define the log likelihood as going to be a sum of two terms that involve the entropy and the multiple information. But when we analyze these two terms, we're going to see that first, this n here, that is the number of a training case that we have, will not change with the tree structure that we select. So we can remove this. If we look at this entropy term here, look at the equation of the entropy. The equation of entropy for a single variable, right? So it's not the conditional entropy, it's just an entropy for a single variable, does not depend on the parent, it just depends on the probability of the variable that we have. So it will not depend on the tree structure. This n term here will also not depend on the tree structure, it just depends on the size of the training set. So at the end we have this here. So when we maximize this guy, we are also maximizing this. And we are saying that the log likelihood can be maximized by maximizing the multiple information between pairs of variables. There are the variables and its parent in the tree structure. Okay, now that we understand the connection between the t-score and the log likelihood, we can return to the Chow-Liu algorithm and see how it is computed. So you already have a good idea how it is computed, so we can go a little quicker over that. So we have basically a data set, and we're going to build a complete undirected graph over all the variables that we have in the training set. So we have the variables A, B, C, and D, and we're going to be a complete graph. So we're going to have an edge between every pair of variables, and the weight of this edge is going to be the mutual information between the nodes that are connected by the edge. So let's take a look for the computation of this edge here that involves the variables A and B in the next slide. Okay, I will not detail this much because you have already seen this before. Actually, you have implemented this in your assignment. So basically the mutual information involves the probability of X and U, that is here and also here, and the probability of X and the probability of U. All those probabilities computed over the training set. So we have those terms here. We have the probability of A and B. We have the probability of A. We have the probability of B. We have this ratio that's basically the probability of B and A divided by the probability of A multiplied by the probability of B. We have this term here that we apply the log for this ratio, and finally we multiply the log of the ratio by the probability of A and B, and we have this final result here. So we do those computations for every value that we have, so for every combination of values that we have for the variables A and B. So I'm going to have one number for A and B, A and not B, not A and B, and not A and not B, and we're going to sum over all of them. So we're going to sum all those numbers together, and we have this number here. And this 0.74 is this number that goes as a weight of the edge between A and B. We have to repeat these computations for all edges that we have. We have one edge for every pair of variables. So we have this complete undirected graph with weight given by the mutual information of the attributes. Okay, now that we have this complete undirected graph, we need to convert it into a tree structure. And what we do is to use a maximum spanning tree algorithm for doing this task. This algorithm is basically very similar to the classical minimum spanning tree. So we have algorithms like a preen and Kruskal. We can just adapt those algorithms to, instead of working with the smallest weights, then I'm now going to work with the largest weights. So it's going to be a very trivial adaptation of those algorithms. So we're going to generate for us what is an undirected tree. But the Bayesian network is a DAG, so we need to convert this undirected tree into a directed tree. And in order to do that, what we do is to choose one node as a root and direct the edges away from the root. We can select any node as a root. For instance, let's suppose that we have this graph and we start building the maximum spanning tree. So we're going to connect these two guys here, we're going to connect these two guys here, and we're going to connect these two guys here. Clearly this one is the maximum spanning tree. But now we have this undirected tree and we need to select one node as a root. Let's suppose that I select the node B is going to be my root. So I direct the edges away from the root, so that's going to be my directed tree, and this is my Bayesian network. So as you can see, if we had selected a different root, like for instance A is going to be my root, it's going to be a slightly different structure, and we wonder if we select different roots, if the computation of the t-score would change in a way that these different trees would have different maximum likelihoods. But it's not the case, because we have here is the computation of the mutual information. So we have the mutual information here, and the mutual information is a symmetric measure. So the mutual information between B and D is the same as the mutual information between D and B. So if we select this edge here or the edge in the opposite direction, would give us the same mutual information. Alright, so all these trees that we can generate by selecting different roots, they will all have the maximum likelihood among the tree structures. So let's take a look at how we can compute the graphs, the trees using the maximum spanning tree, and also selecting the roots in the next slides. So this is one example. We are applying here the preen algorithm, and the idea is that we start with one node. In this case, we're starting with the node A. We look at all possible connections that we have between A and the older node. So we're going to look at by these edges here, and we selected the edge that has the highest weight. So it is a very simple adaptation, because originally the pring algorithm would select the edge that has the smallest weight. So the edge that has the largest weight here is going to be or this guy here or this guy here. I decided to select this one, right? So we have this first connection here. So now I'm going to look at the connections between A and C and the remaining nodes that we have. So we have this guy here, we have this guy here, and we have this guy, and as well we have this guy here. So between all these possibilities, the one that have the highest weight is going to be this guy here with 0.32. So I'm going to connect this gray side with the white side using this edge. So now I have this situation here. And now again, I look at what are the possible connections between the gray and the white side. So we have this, this, and this. And here we have 0.32, here we have 0.17, and here we have 0.02. I'm going to select the one with the highest value, so it's going to be this one, and we end up with this spanning tree here. Given this maximum spanning tree, now I needed to select the root. Again, I can select any node as a root because we have this property that the mutual information is symmetric. So here we have two options. We have selected B as a root, so I'm going to give directions to the edges going away from the root. So I have this guy going away from the root, this guy going away from the root, and this guy going away from the root. And if we compute the log likelihood, this is going to be the value. So this we actually computed the log likelihood by computing the estimates for the parameters using the maximum likelihood estimates, and going to the training set and computing the likelihood of each case and computed the log likelihood and sum everything together, we got this number here. And if we select the A as a root, so we're going to have this sequence here. So everyone going away from the root. And if you compute the log likelihood, again, it's going to be the same number. So it doesn't matter which one is the root of the tree. Okay, and there is a nice shortcut to compute the log likelihood for a certain tree. We can use this property here that we haven't seen in a few slides ago, that the log likelihood decomposes as the conditional entropy between pairs of variables, the variable x and its parent u. So in this case here, we can use this property. We're going to look at the families that we have. So we're going to have this family here, A and C, and we're going to have this conditional entropy here. We have the family B, and because B has no parent, so B is going to be alone. In this case, we compute not the conditional entropy, but just the entropy. We have this family here that is B and C, so we have this conditional entropy of C given B, and we have this family here that is D and its parent B. So we have also this conditional entropy. And if we compute the conditional entropies, again, over the empirical distribution, that is the count that we can compute from the training set, we get these numbers. We multiply by 5, that's the number of training sets, and we get the same result that we have before, minus 12.1. So in this final slide here, we can compare one predefined structure with one learned structure and see if they match or not. It's not exactly a benchmark here because we are just looking at one specific case, but they're going to give us a little bit of an idea if what we learn would be also what we expect if you have built the Bayesian network by hand. And one good example is the ICU alarm network. So the ICU alarm network is a Bayesian network that was built by hand. So every one of the nodes, the connection between the nodes, and also the probabilities, the parameters, were all specified by experts. So as this network was completely specified by humans, so we don't have the training cases. But what we can do, and okay, I'm gonna admit that is a little bit of cheating, we can use forward sampling to generate a training set. So what's exactly what we did here? So we use forward sampling and we come out with a training set for this Bayesian network. And now that we have the training set, we can use the Chow-Liu algorithm to learn the structure for the data. And we can compare the learned structure with the original structure that was specified by the experts. And what I did here, I just marked the edges they match between the tree structure and the original structure, and also I draw some spurious edges that were inferred by the Chow-Liu algorithm but were not present in the original graph. So we can see here that there are many green edges, so there is a matching between the two structures, but there are a few, actually three structures edges that are spurious. They were created by the Chow-Liu algorithm but were not present in the original graph. Of course, because we are creating a tree structure and the original ICU network is not a tree, it's a graph, there will be quite a few of edges that are in the original network but they are not in our network, because the tree structure has a minimum number of edges, right? If we remove one edge, we're going to disconnect this structure and we'll transform this tree into a forest. But if we add one edge, we're going to transform the tree into a graph. So in order to be a tree structure, it must have the exactly minimum amount of edges that will generate this structure that is not disconnected and at the same time it has not a loop. Alright, I think that is enough for this first video. Let's take a break and we'll continue in the next one, discussing how we can now create graph structures. So see you soon.